Up. Thanks for coming. So this is our first of potentially 2 review classes, depending on how many people are here tonight and how many people are here at Thursday night. So there are a couple of things. So first, I didn't hear any feedback for the Tuesday, August 9th exam. I'm assuming that works for everybody. I'm thinking to start maybe at 5:30, and I'll announce that. And if anybody has issues with that, then they can, we can move the start times around. But I think nominally we'll start at 5:30. If you have accommodations and would like to start at a different time, please just let me know. Unlike the midterms, so it will be similar to the midterms, but instead of having just 2 long answer problems, we will have 3 long answer problems. So it will still be gated, just like it was before, where we'll release the different problems at different times. And just for the benefit of those coming in, I think I'll nominally have a start at 5:30, but if you have a conflict with that, just let me know and we'll find a start time that's suitable for you. So again, all the cycles will be covered. 3 of them will be covered in the long answer problems, and the rest will be covered via multiple choice questions. So, not too much, well, there's no new material today, right? We're sort of go over some problems that people had suggested. But these are basically the 5 cycles that you need to know. Although here it only shows a diesel cycle. So you should know how to do auto and diesel. So that's, I guess, 6 cycles. Keeping in mind that this could be a refrigeration or a heat pump cycle. But the analysis is almost exactly the same. It just depends on whether the energy benefit is the heat on the hot side or the heat on the cold side. So these are the things that you want to know. Auto, diesel. You want to know Rankine, including reheat and regeneration. You want to know Brayton, including reheat, regeneration, and intercooling. You want to know how to do turbojets, and then how to do refrigeration and heat pump cycles. So those, if I give you a problem on the exam, I'll give you the option to do it on the tables or on the graph, or at least if I give you the graph, I will still give you the option to do it on the table. So you should probably know how to do both. Personally, if I was given the option, I would do it on the graph because I believe it's significantly faster. All right, so I have, I think, maybe 10 more slides or something, just to kind of brief overview of how we solve these cycle analysis problems, how I try to, in my head, collapse all of these, whatever we said, 6 cycles down into really just one problem where I just making different decisions along the way, right? So we've kind of gone through this checklist of what to do if you don't know what to do. So hopefully next Tuesday, you won't be in this situation, right? But you could open up a problem and feel like, oh, I don't know how to do this. Or maybe this is more complicated than any version of this type of cycle that I've done. And that's kind of scary because it's not something I've seen before, right? So the first thing you want to think about is what kind of cycle is it, right? So, and what's the energy benefit and what's the energy cost, right? The only exception to this would be a turbojet engine, where we won't talk about thermal efficiency of turbojet engines. Otherwise, if it's a heat engine, something that's burning heat to generate power, then you want to have the thermal efficiency, which will be the net work divided by the heat rate in. And if it's some kind of a temperature control device, it'll be the heat rate that you're interested in. So that's the heat rate out of the cold place, if it's a refrigeration cycle, the heat rate into the hot place, if it's a heat pump, and that'll give you a coefficient of performance. Then, at least if it's appropriate, I guess if it's an internal combustion engine, this one you can kind of skip in an internal combustion engine because the mass just all stays in the cylinder, piston cylinder assembly, right? But if it's not, you want to do conservation of mass on all the elements. You want to do a first law analysis on all the elements, or you could say all the processes or all the components, right? And then if there's some part where it says, oh, demonstrate that this process is possible, right? Then you'll want to do the second law on that particular component, right? And then this is often the part that takes the longest time, is you're going to have to fix a bunch of states. Now, if it's like, for example, the Rankine cycle that we'll talk about today, and it's super complicated, and there's lots and lots of states, right? Or if it's like that Brayton cycle we did before that had like 14 states, I think, when you included real and ideal turbines and compressors. You know, if you look at something like that, I think maybe the natural thing is the first look, you know, sort of feels overwhelming. But look at the state table, because the state table will often be partially and potentially most of it could be filled out, right? So that's good, right? So you got to know how to fix the states. And then once you fix the states and you have symbolic solutions, then you can go back and find things like power or net power or heat rate in or heat rate out, right? And then you can find this characterization parameter, either this thermal efficiency or this coefficient of performance. You might be asked to compare that to the Carnot efficiency, which will be related to the temperature in the reservoirs, the high temperature and the low temperature, or the Carnot coefficient of performance, which again, you can relate back to those temperatures. Right, but again, this is kind of a long list for me. So I break these three questions down into a couple of things. So first, the stuff about characterizing the cycle, right? So that's what's the right characterization parameter, and then eventually what's the number, and then is it better or worse than the ideal case? It should be worse than the ideal case, right? And then there's this other question that we had was, is the system open or closed? So when we look at the different processes in the cycle, are we going to use the open version of these governing equations that we have, or the closed version, right? That'll tell us what equations to use. And then we're going to ask, what's the fluid? Because without knowing what the fluid is, then we can't fix the state, right? So to me, when I look at all of these cycles, there are three different questions that I ask. And the answer to those three questions kind of plots out the map for me of how I'm going to solve the problem. And all of these different cycles we did have some similarities and some differences with the permutations of the answers to these three questions. Right, so how do we characterize the cycle? That's our first question. Right, so what are we trying to find? Right, so we need to know the energy benefit and we need to know the energy cost. Right, and if I know those two things, that's going to tell me the thermal efficiency or the coefficient of performance. Right, so I can group these cycles that we've done by the energy benefits, right? So if it's a heat engine, the energy benefit is either going to be work, right? If it's an Otto or a diesel cycle, we'll probably be calculating net work, right? Because it's closed systems. Or if it's a Rankine or a Brayton cycle, it's going to be net power, right? If it's a turbojet engine, really it's thrust power. And we talked about that in class, but I won't test you on that in the exam. So you don't have to worry about calculating thrust power. But if it's a temperature control device, like vapor compression refrigeration or vapor compression heat pumps, then you got to know what's the heat transfer rate that's most important for that cycle. Brayton refrigeration is on this list because once upon a time, we also looked at a different type of refrigeration cycle, but we don't do that anymore. So it's one less thing that's testable on the exam. Similarly, we can look at the energy cost of these different cycles. And the good thing is for the heat engines, it's all heat in or heat rate in, right? So we got to burn something or running some kind of nuclear reaction. We're doing something that's generating heat, and that's an input into our cycle. For the temperature control devices, right, they're like that Clausius machine that's pushing heat the wrong way. And so you've got to put work in to make those cycles work. right? So there's some similarities in cost, and there's some similarities in benefit. So next we got to think about which of these cycles are a series of open systems and which are a series of closed systems. Because if it's a closed system, I have one version of the first and second law. And if it's an open system, I have different equations for the first and second law. Even though the concepts are still kind of the same, right? We conserve energy and entropy is increased. So we only talked about two cycles that are closed. Those are our two internal combustion engines, the Otto and the diesel cycle. Everything else was open, right? So Rankine, the refrigeration and heat pumps, Brayton, jet propulsion, and again, we didn't talk about Brayton refrigeration in this class. And then what's the fluid? And in a lot of cases, this is the one that ends up being the most work for us, because this is sort of like, how do we fix the states, right? So we want to ask, is it something that goes back and forth across a vapor dome? So the working fluid is water or a refrigerant. Or is there no vapor dome? Is the working fluid some kind of ideal gas like air? Right, so if it's liquid, right, something that's got liquid and vapor and they're condensing and boiling, then you've got Rankine and the heat pump and refrigeration cycles. And if it's air, it's everything else, right? So it's Otto, diesel, Brayton, and turbojets, right? So that's, and again, hopefully we're starting to see how all these things converge. But that's all that I wanted to do just for kind of general review. Right, so next, I did want to talk about some problems, but maybe even before we do that, if you have just kind of general questions, either about the exam or about some material, I'm happy to kind of answer those first if people have those types of questions. But if not, that's okay too. So I had asked for volunteers to give me problems. And last class, we had this one that was given to me as a Rankine cycle problem. Now, I find this diagram a little bit confusing. I think what's going on in this first turbine is that there's actually two turbine stages here. We would typically draw it like this, where this mass comes out here, right? And that goes to this open feed water heater. This mass comes out here and gets reheat, comes in here. And then again, there's another two turbines, right? And then this one goes to this open feed water heater system. This one goes to this open feed water heater system. And there's a condenser. But I wasn't exactly sure based on this diagram. So I fished through the textbook and found one that I think is pretty close to the same, but maybe has a little bit more diversity in it because there's a closed feed water heater system and an open feed water heater system. It's still got four turbines, which this one looks like it's only two, but there's two, it's kind of split in half, each one of these, and it still has reheat. So I think this has pretty much all the same the same types of parts of this problem, but not quite exactly the same. But I think, because I understand what this diagram is saying better, that I'd rather do this one than this one. So, my first question is, how do I characterize the system? All right, so this is Rankine, which is a heat engine. So the benefit, well, first that means we're talking about thermal efficiency. The benefit is W dot net, and the cost is Q dot in. Right, so now if I'm going to do this, this means, right, this is the sum of the turbine powers plus the sum of the pump powers. Right? Turbine powers are positive, pump powers are negative. So when I add these together, I get less than the powers developed by the pump. And then I got to remember, because there's some reheat in here, I add up all the places where I'm adding heat. Right, so here this is going to be W dot T1 plus W dot T2 plus W dot T3 plus W dot T4. But there's two pumps plus W dot P1 plus W dot P2. And again, I'm expecting these two here to be negative, but the rest to be positive. Now, where do I add heat? I add heat over here. So this is going to be Q dot from 3 to 4. That's the reheater. But then also Q dot from 11 to 1. That's the main heat, right? But now, so this is good. So I asked, right now I'm going to say, is the system open or closed? If I'm not sure about this, right, then it's all the processes happen in a different place. It's like an assembly line. That means it's a series of open systems. So my first law here is going to be dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in plus V in squared over 2. Looks like it's metric, so it's just over 2 plus G Z in minus the sum M dot out H out plus V out squared over 2 plus GZ out. Now, I also know that dM by dt is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. This is the unfortunate part of this problem because I start to see that I'm splitting the mass here, right? So there's a couple of masses that I need to deal with, right? So I've got this Y coming through here, right? Because I always say, right, bring your pencil crayons. We can even go darker than that so you can. That means that through here, this is 1 minus Y up here, in through here, into this turbine, to here. Now, we've got this other thing, Y double prime, right? And they call this Y prime, right? So then we've got some other, I don't know, let's go purple, right? So now we're going to come through here, down through the condenser, up through here. Now, right, so this is coming in. We've got 1 minus, coming through here, we've got 1 minus Y prime plus Y prime. So this is going to be back to, and then over here, this is tricky, right? So I didn't completely draw this, right? So my Y comes down through here. So all the mass gets back together over here. And now we'll get this color for 1. We'll take orange to be the entire mass flow rate. And we come through here, through the first turbine. Right, so now I know that I'm going to have different mass flow rates associated with the different parts of this problem. Right, but still, when I go through all of my components, they're all steady state. They're all one inlet and one outlet. Even though the mass splits, we always draw the mass splitting at nodes, which is different than in the original drawing, right? At these nodes in between, right? We're going to neglect kinetic and potential area energy everywhere. For the turbines, and pumps, we're going to say that they're adiabatic. And for the and for the boiler and the reheater, they're going to be passive. Right? So that means if I've got a turbine and pump, I'm going to have W dot is equal to M dot, whatever the mass flow rate of whatever that, I'm going to call it, well, I'm just going to say mass M dot here, because if I put a subscript I in it, I don't want to get confused with in, right? And this is going to be H in minus H out. But if I'm trying to find a heat transfer rate, that's going to be M dot times H out minus H in. And those are the equations that we're used to, right? But now comes the hard part, because these mass flow rates are potentially different for all the different components. Right? So now when we go to our thermal efficiency, which was the turbine power plus the second turbine power, 3 plus W dot 4 plus W dot P1. Oh, these are all turbines. Plus W dot P2 divided by Q dot of the boiler plus Q dot of the reheater. Now over here, I'm going to redraw the picture. So my first turbine gets all of that mass flow rate. Right, so this is going to be, oh, that's pretty thick. M dot, they're all times the total mass flow rate. And then the first turbine is going to be just 1 times H in minus H out. So that's H1 minus H2. But my second turbine gets 1 minus Y prime. And this is going to be H2 minus H3. My third turbine also gets 1 minus Y prime of the mass flow rate. But H in is now 4 to 5. So this is H4 minus H5. Then my fourth turbine gets, let's see if I can squeeze it, 1, minus Y prime minus Y double prime times H in minus H out, H5 minus H6. So that's my turbines. But now I've got my pumps. So my first pump, right, gets that double diverted mass flow rate. So 1 minus Y prime minus Y double prime times H in minus H out, which is H7 minus H8. But my second pump gets all the mass flow rate. So it's just going to be H9 minus H10. So that's my numerator. My denominator is going to be all of the mass flow rate times H out minus H in. So this is H1 minus H11 plus, and then here I have 1 minus Y prime in the reheater times H out minus H in, H4 minus H3. I see that my mass flow rates cancel, right? And I got an equation. So the good news here, right, is I have a whole bunch of H's. So if I could fix all the states, I'd be pretty good. But I also need to find my Y's and my Y primes. Right, so here what I need to find, H's, Y prime, and Y double prime. I personally would probably start trying to find the H's. Now there might be some intermediate steps. If you got this, it might say something like, oh, what's the net power, right? Or it might say, what's the back work ratio, or right? So, but ultimately, all of those equations get calculated by using these equations, right? We use the first law to get symbolic solutions for each of these components, which end up being not too bad, except we got to just account for the fact that there's different mass flow rates everywhere. Right? Another thing actually that I haven't done yet here that I probably should show you how to do is let's draw, you might be expected to draw a TS diagram here. TS diagram is going to be a little bit messy for this one because there's so much going on, right? So we have water is the working fluid. If water is the working fluid, that means you draw a vapor dome. How many pressure lines do I draw? Okay, well, I want to look to see, right, how many turbines. So turbines, I have 4. Pumps, I have 2, right? So I take the maximum plus 1, so I need 5 different constant pressure lines. So this is going to be P1, right? And then we go through some turbine. Oh, that lowers our pressure. P2. Then we're going to go through some other turbine, which lowers it to P3. So that's 1 turbine, 2 turbines. P4. Oh, I guess the numbers kind of changed because we reheated in between, right? So this is P1. P2 is less than P1. P3 is less than P2. But P4 is the same as P3, right? So this should be P5. And then we go through this other turbine, and that gets us down to P6. So usually I don't draw the mass splitting on these, right? So my state 1 is here. If this was an ideal turbine, it would come to 2S. But if it was a real turbine, it would come down here to state 2. And then I just go through another turbine, even though the mass split, right? So I would say this would be state, this would 2 to 3S. And then the real turbine would go to state 3. But then what happens from 3 to 4, I add heat. Anytime I'm adding heat, I move from left to right on a constant pressure line. So this is going to be state 4. And then this would be 5S and 5. Again, we go through a turbine from 5 to 6. So this would be, if that was a vertical line down, 6S and 6 is over here. Now what happens from 6 to 7 is we condense. And we always assume when we condense, we're going to condense right down to the saturated liquid. You could go further than that, but then you're losing more heat that you just have to put back in. So you don't want to condense further down than the saturated liquid. Now we see when we get together here, so this is state 7 is the condenser. The pressure goes from up now, right? So this is the opposite of the turbine. So this was going to go up. But where does it go up to? See how this meets with state 5? That means they have to be at the same pressure. So state 7 and state 5, or sorry, state 8 and state 5 have to be the same. So this would be 8S and 8 is to the right of that. And then we heat up from 8 to 9. So this is on the constant pressure line. I didn't really give myself enough space. But 9 would be somewhere over here, right? Again, on the constant pressure line, going from left to right. And now we pump up again. But now we're going to pump up all the way to P1. So this is state 10S all the way up here. And then we get some heat. Oh, and I guess state 10 is a little bit to the right of that. We get some heat here. I don't know where this state's going to end up. I'll draw it under the vapor dome. I could be wrong. It's 11. Right? And then as we move from 11 to back to state 1, then we come here. Now somewhere in here, we've got some of the mass going from state 2 to state 12. So that stays at the same pressure. There's some, I don't usually draw this, right? But so that cools down. So it's going to come maybe over here, somewhere here is like state 12. And then we drop the pressure from 12 to 13 back to this pressure down here at state 5. That's some isenthalpic thing. So I'm going to draw it. I know the entropy has to increase. So I'm going to call state 13 over here. But if you didn't draw state 12 and 13 on your TS diagram on an exam, that's okay. So that's kind of how I would go through drawing the TS diagram. Does anybody have questions about that? Because I know it's kind of a complicated cycle. Okay, so let's go about fixing the states. I just like to keep... So here we'd have a state table. And again, if this was an exam, a lot of these states would be filled in. But I'll talk conceptually about how to find all of these states. Right, so here we see at state 1, they definitely give us the temperature here. I don't have necessarily all the given information. But I'm going to say they give us the temperature and the pressure here. So here, probably this is going to be a superheated vapor. It could be a saturated vapor. So that means I'm going to go to table A4 and find H4, or H1, sorry. But I'm also going to find S1. As I move from state 1, I don't exactly go to state 2. First, I go to state 2S. Let's say they give me the isentropic efficiency of the turbine. That's going to be the real power over the ideal power, which is m dot H1 minus H2 divided by m dot times H1 minus H2S. It only makes sense to compare the real and the ideal turbines if they have the same pressure difference and they have the same mass flow rate. So the mass flow rates cancel. There's two things that I could ask you here. I could ask you what the isentropic efficiency is, and I could ask you what the what H2 is. Either way, you're going to have to find H2S. So for that, we know that S2S is equal to S1. And then I have to say at P2 is S2S. Well, I guess we draw it like this, right? Oh, maybe I'll do a number line. That's my terrible number line. Looks like also a terrible skateboard. Right, so this would be SF, and this would be SG. If it's in between these two things, that means it's two-phase. Find X2S. But if it's over here, that means it's superheated vapor. Find, so you'd have to just interpolate, right, to find S2S. Right? And then once you have S2S, on whatever table you're at, you interpolate to find H2S. Now, if I gave you the isentropic efficiency of the turbine and you found H2S, then you can find H2. But if I gave you H2, you could find H2S and then find the isentropic efficiency of the turbine. Right? But let's assume in this case that this was given. Right? So now once I find H2S, I can go from 2S to 2. And now from here, I use the isentropic efficiency of the turbine to find H2. Does that part make sense? Good, because we're going to do it 4 times, right? Which is exactly why I wouldn't make you do it 4 times on an exam, right? So even though you might have a really complicated problem like this, maybe I've asked you to find H2, but I tell you H3, H5, and H6, so you don't have to do the whole thing 4 times, right? Because I want to see what you know, and that's better for me to ask you a bunch of different things instead of the same thing 4 times, right? But as I move from state 2, now I can go to state 3S, and we do the same thing again, right? S3S is the same as S2, and then you can determine, is it a 2-phase mixture or is it a superheated vapor? And you can find S2S and then H2S. And then as you go from 3 to 4, or 3S to 3, then you can use the isentropic efficiency of the turbine to find H3. Now usually, and you can see they did it again in this problem, so if you get stuck, if you get bogged down somewhere over here, go to the next place where they tell you the temperature. Because the states where they tell you the temperature are the best states, right? Because now I can go from 3 to 4, temperature is known, and usually the pressure will also be known. Although they might just tell you the pressure at 3, but you say, oh, this is a heat transfer process, so I'm going to assume that the pressure stays constant. So then you're going to see what's the phase, right? Probably this is also going to be superheated vapor. I'll put a question mark here. Could be saturated vapor. And then I'm going to find H4, and I'm going to find S4. And then again, I'm going to go to state 4S, right? And I'm going to say S4S is equal to S4, right? What's the phase? And then I'm going to find H4S. Sorry, I'm going 4 to 5. This should be state 5S, S5S, and this will give me H5S. And now here, I'm going to go from 5S to 5, right? And I'm going to use the isentropic efficiency of the turbine to find H5. And because I'm not tired of doing it yet, I'm still going to go and do it again as I move from state 5 to state 6. I go through a turbine again. Right, so 5 to 6S, S6S is equal to S5. Find the phase, find H6S, H6S to H6. All right, now we're going to use the isentropic efficiency of the turbine to find H6. And now we're finally done with the turbines. Now, as I go from 6 to 7, this is condensation. Typically, we will know P7, which is equal to P6, right? Here they tell us the condenser pressure, right? And then we're going to say that we're going to go right to saturated liquid, right? So H7 is equal to H7S, or sorry, H7 is equal to HF at P7. And if I wanted to know S7, it would also be equal to SF at P7. Now I can go through the pumps, right? So now as I go from 7 to 8S, here I know this is not just, I got to ask myself, what's the fluid, right? Oh, it's liquid. Oh, am I going from liquid to liquid? Yes. Am I going through an ideal pump? Yes. So this is ideal pump, right? So now as I go from here, I know that delta H, which in this case, probably we're trying to find in minus out. So let's call this H7 minus H8S is equal to the specific volume at state 7. So here I also want to find VF at P7 times, same order here, P7 minus P8. Notice that P8 is the same as P5. Because anytime you come together in an open feed water heater, everything has to be at the same pressure. Otherwise, you'll get backflow. So if this was like screaming in at some super high pressure, then that flow's going to, some's going to go in here, some's going to go down here, some's going to go down. It's not good, right? So that's why we have this trap here. Remember, traps are like the valves in those heat pump cycles where nothing changes but the pressure. So this is good. This will give me, I could work out H8S here, but I actually don't necessarily need to, because here I'm going to talk about the isentropic efficiency of the pump, right? And the isentropic efficiency of the pump will tell me something, right? So it's going to say, again, it's power over power, but this is an energy cost to the system. So the ideal pump is here and the real pump is here, right? So here now we're going to know something about this. So the ideal pump is going to be, right? We said delta H, right? Because this is going to be m dot times H7 minus H8S over m dot times H7 minus H8. But this is specific volume at 7 times P7 minus P8 over H7 minus H8. So I never really actually need to find H8S, right? I can use, if again, it could be structured so that I know H8, or I have to find H8. Right, so we use this expression. Let's say that if I know this, right, then I can find H8. Now it starts to get a little trickier, because as I go from state 8 to state 9, I don't exactly know what's going on there, right? Oftentimes I will be given some information about these states, but one thing I can do for state 9 is I can use the first law. Anytime you have a component that's got more than one inlet or more than one outlet, be prepared, because you might have to do the first law on that component. Actually, you will probably have to. If you see one of these Rankine regeneration problems, expect to do the first law on at least one of the feed water heaters, probably both of them. Right? So here, right, I can say that dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in plus V in squared over 2 plus GZ in minus the sum M dot out H out plus V out squared over 2 plus GZ out. Here it's steady state, it's adiabatic and passive, as long as it doesn't tell me, oh, there's some heat loss from the heat exchanger, right? I'm going to say that there's no kinetic energy change, no potential energy change. And what I get is that 0 is equal to the sum of M dot in H in minus the sum of M dot out H out. And as long as I use my pencil crayons here, then this is not intimidating, because I've got a color pegged to each mass flow rate, right? So this is all going to be the total mass flow rate times the inlets. So this is going to be y double prime times H5 plus H8 comes in here at 1 minus y prime minus y double prime. Right? That's going to be times H8 plus, there's another inlet here, which is going to be y prime times H13. And then there's one exit, that's the whole mass flow rate times H9. Right? So we can't really use this equation yet. The good thing though, I can cancel this out. But there's a lot of unknowns here, right? Probably we won't know y prime yet. We do know H5 because we found it. We don't know y prime or y double prime. We do know H8. We don't know y prime. We don't know H13 yet. We don't know H9. But often in a problem like this, it will say something like H9, that this is a saturated liquid or something. That you're saturated liquid before you go into this pump. And if that's the case, then here you would be able to get H9 would be equal to HF times, or just be HF, right? So maybe that gives us H9, but we still don't have this other stuff yet. Right? So we can't use this equation to solve for one of these prime numbers yet. But H9, usually we're given enough information to solve H9. But you can see there's different permutations of information that you can get, right? But these are the equations that you use no matter what inputs you have. And then as we go to state 10, I'm just going to skip to this formula again. We have the pump efficiency, which is the ideal pump divided by the real pump. And this again looks just like this. This is going to be the specific volume at 9, which is going to be probably VF at P9 times in minus out. So P9 minus P10. It's important you get the order right, because otherwise when you're solving for that other enthalpy, you'll get the delta wrong. So the H should be going up through a pump, but down through a turbine. So this will be H9 minus H10. And again, oftentimes you know this, you can get all this stuff, and you find H10. Now, you can see here at H11, they told us the temperature. Probably that means in state 11, I think when I drew the TS diagram, I drew it as being under the vapor dome. But it's probably just going to be super cool or subcooled liquid. It probably hasn't started boiling yet. But here we'll know P11 and T11. Usually this will still be a subcooled liquid. And for subcooled liquids, H11 will be approximately equal to HF for T11. So that would get us here. And that's not bad, right? We still need 12 and 13, but 12 and 13 are the same. So now how do we get to state 12? Right? So we know that H12 is equal to H13 because they're just going through a valve there. So isenthalpic. Delta H is equal to 0. But we don't know either of those two things yet. And there's a couple of different ways that this type of problem could be asked. Right? So usually the answer here is, again, to use the first law. So as we move through here, if I use this as my control volume, it's going to be just the same equation that we got there. So the CV is the now closed feed water heater. So this is going to be steady state, adiabatic, passive. It's not one inlet, one outlet, but we're going to say that the change in kinetic energy is approximately equal to 0, which is equal to the change in the potential energy. And what that's going to tell us is that 0 is equal to the sum of m dot in, h in, minus the sum of m dot out, h out. This is a common equation for heat exchangers when we know information on both sides and we're not solving for Q dot. So what are we going to do here? Right? We are going to, I like to group them in a closed feed water heater by the mass flow rate. So this is going to be 0 is equal to the total mass flow rate times, well, I guess the total mass flow rate is going to be times everything, right? But I'll use the orange line first. From it's still h in minus h out, so this is going to be h10 minus h11 plus y prime times the mass flow rate, which is going to be h2 going in minus h12. The mass flow rate cancels, the total mass flow rate, right? I know h10 already, I know h4, and I know h2, but I don't know y prime, and I don't know h12. So the problem is going to have to give you one of those two things. I think, again, oftentimes you might say, oh, this comes out as a maybe a superheated vapor, maybe a two-phase liquid, but you go through here and it comes out maybe here, and maybe it says X12 is equal to 0, right? That it's a saturated liquid. Or at least it gives you enough information. So here I'm looking for state information. For example, if X12 is equal to 0, then H12 is going to be equal to HF at P12. Right? And remember P12, which is the same thing as P2. And then once I find H12, right, as I go from 12 to 13, H13 is equal to H12. And this is when it all starts to roll up. So if I know H12, then I can use this equation to find y prime. Right? If I'm looking for mass flow rates, remember, and if I'm trying to find the diverted mass flow, then that's looking for a mass flow rate. I only have three options, right? I can look for some place where I know the area times the velocity over the specific volume, which is the same thing as the volumetric flow rate over the specific volume. Or if they told me something like a net power or power through one of these turbines in a heat rate, then I would use the first law to get some equation that had, that had that component in it, right? Or I can look for some place with more than one inlet, more than one outlet, and do the first law. Right? But if I have a choice, I want to minimize unknowns. So when I look at this equation, I only have y prime. I don't have y prime and y double prime, so I would do this one first when I'm doing this first law, right? Because both of these feed water heaters, right? So when I'm thinking about a Rankine cycle with regeneration, this is a feed water heater. I'm always going to have to do the first law on the feed water heater. So if you get lost, you don't know what to do, you see one of these problems, do the first law on a feed water heater, right? What can sometimes happen in these two is that they don't tell you state 11, right? But they do tell you state 11 is here, right? This is not a 4. but they do tell you Y, right? So they might tell you Y prime, but not state 11. And then it's still the same thing. You use the same equations. It's just different permutations of inputs, right? So minimize the unknowns. You do this one first, right? So once I know H12, that's good. Then I can find Y prime. Then I can go back to the first law I did on the other one, right? And now I didn't know H13, but it's the same as H12. I do know H9 now, right? I do know Y prime now, so then I can use this ugly equation to isolate for Y double prime. So that's generally how you do these Rankine regeneration problems, is you look for the state information that you have. You look for ideal turbines and pumps, and maybe isentropic efficiencies, because they'll help you find the real turbine and pump outlets. And then you do the first law on the feed water heaters, because that's going to tell you either some other piece of state information, or, and this is maybe more likely, you're going to get the diverted mass flow, either Y, or if it's a crazy one like this that has two different mass flow rates or diverted mass flow in more than one place, then you can do the first law there to find those. But if you get in a case like this and there's two feed water heaters, start with the one that has the fewer colors touching the inlets and the outlets. So does anybody have questions? I know it was pretty high level and we didn't get into numbers. Does anybody have questions about this Rankine regeneration problem or about Rankine cycles in general? All right, let's try to take five. Let's go to 7:35. We'll take a break and come back then. Thanks, everybody. All right, thanks for coming back, everybody. So the next cycle that I wanted to go over was a turbojet cycle, but this one's going to be a little more complicated than the one we did in class. Because in the one we did in class, we had ideal compressors and turbines. But in this one, I want to say that there's a real compressor and a real turbine, right? Maybe I'll draw the TS diagram first. But let's say that we know this compressor efficiency and we know this turbine efficiency. Now, I've left this mostly blank here, but let's assume again that we know the initial temperature and pressure, right? One of the things that we know is that the pressure at the inlet is the same as the pressure at the outlet. So P5 is equal to PA. And we also know this compressor pressure ratio, P2 over P1. I think, and we're also given the maximum temperature in the engine, which is the temperature going into the turbine. And I think if we know those things, then we'll be able to do the whole cycle. So again, I look at, this is a little trickier when we think about the number of pressures that we need. Because I've been saying the number of compressors and the number of turbines, but it's really the number of compressors plus the number of turbines divided by the turbines, or compressors plus diffusers and turbines plus nozzles. Because they kind of do the same thing. Diffusers increase the pressure, just like compressors or pumps. Turbines decrease the pressure, and so do nozzles. Right? So this is 2 over here. This is 2 over here. So I need 3 different pressures. I need my lowest pressure, I need my highest pressure, and I need some intermediate pressure. Here we're going to start at state A. We go up to state 1. I guess this would be 1S, I'm sorry. So we'll have a dashed line here up to state 1s. But then the real one, no, we'll do an isentropic diffuser and nozzle still. So this will be 1s, which for our purposes is the same as state 1. But then state 2 coming out of the compressor, 2s, and then state 2 over here. Then we heat up, which means constant pressure. So we move from left to right over here to state 3. We go straight down to state 4s, or down and to the right to state 4, and then we go straight down to state 5. Right, so here, if I was drawing this, this would be kinetic energy in, kinetic energy out. I have power coming in, power coming out of the turbine, and I have heat coming in. And the special thing about turbojets is the real compressor has the same power as the real turbine. We're only running the turbine so that we can run the compressor, because we want to maximize, we want as much enthalpy at state 4 as we can, because we're going to turn that enthalpy into velocity. Right? So this is a critical thing to remember about Brayton cycles. So state A is essentially known because we know the temperature at A and we know the pressure at A. That means that if it's constant specific heat, do you have a preference if I do constant specific heat or variable specific heat? Does anyone have a preference? Okay, I think in the notes when we did the problem for turbojets, I believe it's done both ways in that problem. So I think I'm going to do constant specific heat because then I don't have to flip back and forth through the tables. But anytime I use an isentropic relationship, it just means you use the PR over PR instead of T over T is equal to P over P to the power of K minus 1 over K. Right? So here, if this is constant specific heat, I'm done. Because all I need is the temperature and the pressure. If it's constant specific, I don't need H, I don't need U. I guess I'll need velocities. Oh, I guess here we also needed to know the velocity at A. Right? Sometimes given as the jet velocity. Remember in these problems, we always assume the air itself is still. So if you know the jet velocity, we assume that that's the same as the velocity of the air coming in this moving frame of reference. Now, as I go from state A to state 1, this is an isentropic diffuser. Which means that I can write down my isentropic relationship. So delta S is equal to 0. That's great when delta S is equal to 0 and the working fluid is air. So I guess my 3 questions, right? So how do I don't have to worry about how to characterize this, except that the energy benefit is thrust. So I'm trying to get the maximum velocity out the back of the jet as I can. And the energy cost is that I'm burning heat, right? That's my first question. My second question, is it open or closed? So it is open systems. And the working fluid is air. So because of that, I can use the ideal gas law. So I'll say that I assume that it's ideal gas, right? And I'm looking for where delta S is equal to 0. Right? So as I go from A to 1, we'll say that that is an isentropic process, which means that I can say T1 over TA is equal to P1 over PA to the power of K minus 1 over K. And this would be an excellent equation to use, except I don't know T1 or P1. I know PA, and I know K is 1.4. Right? So I can't use this yet. But anytime you're doing a nozzle or a diffuser, these are where kinetic energy is important. The job of the diffuser is to take this kinetic energy associated with this inlet velocity and turn it into more enthalpy at state 1. So I'm going to use the first law. I'm going to say for the diffuser, this is going to be at steady state. It's going to be adiabatic, passive, one inlet, one outlet. The potential energy change doesn't matter. And I'm going to say anytime I'm inside the engine, the kinetic energy doesn't matter. Kinetic energy is important at the inlet and it's important at the outlet. But we'll say that the diffuser slows this velocity down enough that the kinetic energy doesn't matter that much. So the first law that I'm left with from the diffuser is that 0 is equal to m dot times, at the inlet, I've got HA plus VA squared over 2. And at the outlet, I just have H1. This should be m dot out and H out over here. Right now, the mass flow rate doesn't matter here because everything is multiplied by the mass flow rate. I'd like to do two things here. Because this is a cold air standard analysis, I'm trying to get delta H and turn it into Cp times delta T. Right? But I don't know the velocity. So I also want to isolate velocity. So this is going to be VA squared over 2 is equal to, I got to move the enthalpies over to the other side. So this is going to be H1 minus HA, or Cp times T1 minus TA. Now, even in the metric system, which is the preferred unit system, units are a problem with kinetic and potential energy. So Cp is in kilojoules per kilogram Kelvin. It might be given like it is here, or you might have to find it, I believe, on table A20 for different gases. And this temperature is in Kelvin. That cancels out. So this is kilojoules per kilogram. But if I take this, velocity squared is meters squared per second squared, right? Which is the same as meters per second squared times meters, right? But Newton told me that weight was equal to mass times acceleration, right? Or acceleration in terms of g, right, is equal to weight over mass. So this is also equal to newtons per kilogram times meters. Newton meters per kilogram is joules per kilogram, but I want kilojoules per kilogram, so then I have to multiply this by 1 kilojoule per 1,000 joules. So the joules are going to cancel, and this is going to be 2,000. Right? So here, I'm actually given VA, so I'm not solving for VA, but I had to arrange the equation this way because I wanted to get this delta H in here, because what I'm trying to do is use the constant specific heat, right? So now I know Cp, I know VA, I know TA. This lets me find T1. And once I have T1, I can rearrange this equation up here to say that T1 over TA, I have to invert the exponent, K over K minus 1. You can like take the log of each side and multiply, but I never do it that way. Is equal to P1 over PA, right? And that lets you find P1. So in constant specific heat, you're always trying to find the temperature and the pressure at a given state. So that's good. Now we have that, right? So now we can go from state 1. Where's my mouse? Uh-oh. To state 2. And let's see, I got batteries over here. And hopefully, yep, that fixed our problem. So now we're going to go through this compressor. So now we're trying to go from state 1, but first we got to go to state 2s, right? Because we want the isentropic relationship, and we're given an isentropic efficiency for the compressor, right? So this part going up in the turbojet engine is normal, just like it would be for a Brayton cycle, right? So now I ask, is delta S equal to 0? Yes, it is. That means that T of 2s over T1 is equal to P of 2s over P1 to the K minus 1 over K. But this only makes sense to compare real and ideal turbines if they have, and compressors and pumps, if the mass flow rates are the same and if the pressures are the same. So P2s is equal to P2. So then T2s is equal to T1 times, this is our compressor pressure ratio, right? P2 over P1. I'll leave an S here just to remind myself. K minus 1 over K, and this is R, which was given. So here, I know T1, I know this compressor pressure ratio, and I know K, so now I know T2s. And I know P2s is just P1 times R. But that's also equal to P2. Right now, again, this looks kind of normal, right? I want to find the real outlet. The compressor efficiency is the same as the pump efficiency. They're power over power, but the compressor is just like the pump, where it's a cost to the system. So the ideal goes on top of the real, mass flow rate times, well, I'll write it out. So we would do the, right, we do the first law analysis here. So we say that the compressor and the turbine are steady state, adiabatic, one in, one out, no kinetic energy change, no potential energy change. So then that means that W dot is going to be M dot times H in minus H out. Right, so that's kind of what we expect. Right, so this is going to be H in is H1 minus H2S when we're talking about the ideal version. Right, and M dot times H1 minus H2. Mass flow rates cancel. Right, but now I'm going to use my constant specific heat assumption to make this Cp times T1 minus T2s over Cp times T1 minus T2. The Cp's cancel. I know the efficiency. I know T1. I found T2s over here. Right? I know T1. So then I can use this to find T2. And P2 is the same as P1 times R, which is P2s. That part makes sense? State 3 is always my second. Well, actually, in a turbojet engine, state 3 is my favorite state because kinetic energy isn't important and they tell me the temperature. Anytime you have a cycle that uses ideal gas and they tell you the temperature, it means you're done. You fixed that state already. Maybe if it's variable specific heat, You got to go to table 822 and pick off H. But state 3 is great because P3 is equal to P2, which is the same as P2S, which is P1 times R. And because we know T3, then we're done. Right? State 3 is my favorite state. Now here's where it gets tricky. Because next we want to go from state 3 to state 4, right? We might say 4S because we're used to doing the isentropic turbine first. Right? So let's say we did that. Let's say I'm walking down the path. I'm just doing it exactly like I would do a Brayton cycle. And then I would say, oh, is delta S equal to 0 through the ideal turbine? Yes, it is. That means I can say that T4S over T3 is equal to P4S over P3 to the power of K minus 1 over K. And that equation is 100% true. Well, not 100% because it's an assumption. Right? But I know T3, I know P3, I know K, but I don't know T4 and I don't know P4. If this was a Brayton cycle, because the exit of the turbine, or at least the exit of the last turbine, and the inlet of the first compressor touch the same environment. So if this was a Brayton cycle, just a 4-component Brayton cycle, then what we would say that P4 is equal to P1. But in a turbojet, this is not true. This is not 1 over R like it would be in a Brayton cycle. This is one of the things. Sure. Just let me finish this. So this is one of the things that people will consistently make mistakes on in a turbojet problem. Right? So what we need to do is we need to remember for a turbojet, one of the first things we write down is that the back work ratio of the real parts is equal to 1. That means that the power from the real compressor is equal to the negative of the power of the real turbine, which means that m dot times the real compressor is going to be H1 minus H2 is equal to m dot times the real turbine is H3 minus H4. Or, because we're using constant specific heat, m dot Cp T1 minus T2 is equal to m dot Cp T3 minus T4. The mass flow rates and Cp stay the same. Here we know T1, T2, T3. We can use this to find the real outlet temperature. Then we go back and we use the isentropic efficiency of the turbine because we only know the temperature, but we want to know the pressure. But I can't use this equation when I'm going from the real inlet to the ideal outlet. So now I got to use the turbine efficiency, right, which is W dot ideal over W dot real over W dot ideal, right, which with constant specific heat is going to be m dot Cp. The real is H1 or H3 minus H4, and the ideal m dot Cp, T3 minus T4. M dot Cp T3 minus T4S. So I use this equation to find T4S, which I put into this equation. Right? Now I know this, and I use this to find P4S, and P4S is equal to P4. This, I think, is the trickiest part of a real turbojet engine, is that when we're coming down the turbojet engine, it's a bit backwards when we go through the turbine, right? And we still need, so there's a couple of things people will often mess up, right? They'll try to make this 1 over R, which takes too much of the enthalpy away from state 4 and makes it so we don't get good velocity out of the back of the jet, which is the whole purpose of the jet, right? Or they try to use this isentropic relationship going from 3 to 4, which is not an isentropic process. Did everybody get this part down? I was asked to go scroll up to the first page for just a second. So what was the information that we needed on the first page here? So just to recap, what we've done, we did the first law on the diffuser. We used the isentropic relationship over here on the compressor. T3 was given, so we knew this state. And then here, we used that the back work ratio was equal to 1. And then we used the isentropic efficiency of the turbine. And then we use the delta S is equal to 0 equation. Right. I guess here, and then we use the isentropic efficiency of the compressor to find the real outlet. Now we're almost home, right? So we did state 4. As I go from state 4 to state 5, this is the isentropic nozzle. Just like the diffuser, what I need to do is the first law. dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over 2 plus GZ in minus the sum of M dot out, H out plus V out squared over 2 plus GZ out. Let me just, is it still... still here in my clipboard. Yep. Right. So now what we're doing, right, is we're doing a first law analysis on the nozzle over here. So the nozzle is going to be steady state, adiabatic, passive, one inlet, one outlet, no potential energy change. Kinetic energy doesn't matter inside the jet. It only matters outside the jet. So it sticks around over here, but it goes away at the inlet. So this tells us that 0 is equal to M dot, there's only one mass flow right here, H in plus H out minus V out squared over 2. This goes away. Again, we're going to try to group the delta H's, so we want V out squared over 2 is equal to H in, which is H4 minus H5, right? And by constant specific heat, we'll assume that this is Cp times T4 minus T5, right? We also know that this whole part here, just like it was before, is in kilojoules per kilogram, but this is only in joules per kilogram, assuming we're solving for a velocity in meters per second. So if we want a velocity in meters per second, we have to divide by 2,000, right? Which is really the same thing as saying 1 kilojoule is 1,000 joules. This is a great equation. Really like this equation, but I don't have the velocity out, which is one of the things that the problem asked me to find. I do know Cp, I do know T4, but I don't know T5 yet. The trick is that this is an isentropic nozzle. And because delta S is equal to 0, that means that I can say that T5S, which is the same thing as just T5 in this problem because we're assuming it's isentropic, over T4 is equal to P5S over P4 to the K minus 1 over K. Now we found P4. This we know already. This P5S is equal to P1 because they both touch the environment. Or PA, I'm sorry. Because they both touch the environment. That's an A and not a 9. Maybe I'll redraw that. Because my penmanship isn't the best in the best of times. So, writing on this thing is always a bit of a challenge for me. So this pressure is the same here. They were nice enough to tell us that, right? That this was 11.8 PS. Oh, you know what I've been doing? Oh, see? So this is if it's metric. But let's go through the units as if it was imperial, right? Because the picture is imperial, but the data that they gave us for CP was in metric. So if this was in imperial, it's a little trickier, right? So this down here will be in imperial units, right? So here, then CP would be in BTU per pound mass degree Rankine. Delta T would be in Rankine. So this would be BTU per pound mass, which is what we look up H in on the table, right? But it's a little trickier when we talk about this velocity because then the velocity is going to be in feet squared per second squared. But we sort of do the same trick and make this feet per second squared. That's like an acceleration times feet, right? But Newton's second law tells us, and this is where that GC comes in, right? Tells us that weight is equal to mass times acceleration, but we have to divide by that GC thing, right? Because 1 pound mass has 1 pound of force, even though the gravitational acceleration is 32.2 feet per second squared. I can just get the units, right, off the equation sheet, but I'll check it out here because this I know is in pounds force. This is going to be pounds mass, which is the mass out front. The G is feet per second squared. And the GC, I got to get pounds force over here, so it's going to be like feet per second squared. That's going to cancel that out. Times pound mass, because I got to get rid of that in the numerator. And I got to stick pounds force in the numerator, so it becomes the denominator of the denominator, which is apparently tough for me to say. But all this means that feet per second squared is going to be the same thing. So here, if I take this, feet per second squared is going to be equal to pound force over pound mass times can I scroll down here to get it out of the way? Okay, times, and now I got a feet per second squared times pound mass over pound force. So you can see that we can't actually use that, right? Because it just goes to feet per second squared. But we know that what we need here is we have to have this. We want it in BTU per pound mass, right? So we need this guy. We got to first divide by GC, right? Because our term is not just V squared. That's where I messed up, right? because in imperial units, this is going to be V squared over 2GC is equal to CP times T4 minus T5, right? But GC, if I erase this, so this gave us the units of GC, right? But this is going to be, this side, feet squared per second squared divided by feet per second squared times pound mass over pound force. So this is going to cancel out with that, and we're going to get foot pounds force per pound mass. So if this was an imperial unit problem, this would be V out squared over 2GC times 1 BTU over 778 foot-pounds force is equal to CP times T4 minus T5. So it's still kind of the same. It's close to the same, but you got to remember that the kinetic energy term gets this GC in the denominator. That gives us energy per unit mass, but it's not the right kind of energy, so we have to divide by 778 to get BTU, right? But still, when we got to this point, then we didn't know velocity and we didn't know T5. So here, we went up to here, right? And because we know the pressures, we know that T5 is equal to T4 times P5S over P4, K minus 1 over K. That gives us T5, which we can put into here, and then we can find V out squared. So turbojets are tricky. The parts where people most commonly make mistakes, even in ideal turbojets, are units on the kinetic energy terms, even in metric, and that the back work ratio has to be 1. So you don't know the pressure difference across the turbine, right? You need to use the isentropic relationship to find that. And it gets even a little bit trickier if the turbines and the compressors are real, because then you first have to set the back work ratio equal to 1 to find the real turbine outlet. And then you got to use the isentropic efficiency to find the ideal turbine outlet. Only then can you use this isentropic relationship to find the outlet pressure for the ideal turbine, which is the same as the outlet pressure for the real turbine. And hopefully that made some sense. It wasn't just gobbledygook. Okay, so that was that one. I think we had a volunteer to find a diesel engine problem. Were we able to do that or no? If not, when we come back after break, if you can find one, that's good. If not, I'll just sort of conceptually walk through how we would go through and solve a diesel type problem. Yeah, if you could send it, that would be great. And then we can go through it. Or if you just have like a picture of it or something, I think you can put pictures in the chat, but you can do that, or you can send it to me via email. We'll come back at, let's say, 8:17. Okay, thanks for coming back, everybody. Sorry I'm a little later than I think I said, maybe by a minute or so. So here we have a diesel cycle problem, right? So there's a couple things that are important in the problem. So they don't give us any kind of a picture, which sometimes is a pain, but we'll see what we can do, right? It's a little more common, I think, for these diesel cycle problems and auto cycle problems because there's not really a cycle diagram to draw, right? Except the PV diagram, which they're going to ask us to do, right? Expansion stroke of a typical air standard which has a compression ratio of 20 and a cutoff ratio of 2. At the beginning of the process, the initial temperature is something, and air expands at constant pressure until cutoff 2 to 1. Subsequently, the air expands adiabatically, no heat transfer, until it reaches the maximum volume. So sketch the PV diagram. I think for auto and diesel, it's more important to know how to draw the PV diagrams. And for the the processes that are a series of open systems, I think it's more important to know how to draw the TS diagrams. And I'm the person who's going to write the exam, so you should listen to me. Right? So here at state 1 in a diesel cycle, right? The nice thing about the diesel cycle is it's always the same, right? They might give you different inlets or inputs and outputs, but it's not like a Rankine cycle or something where the TS diagram is going to look very different depending on what happens. There's only one kind of diesel cycle, right? And it's got compression from state 1 to state 2, and then constant pressure heat addition from state 2 to state 3, and then it's got isentropic expansion to state 4, and then constant volume heat rejection, right? So this is work. I always like to draw this. Work goes in 1 to 2, work comes out 3 to 4, heat goes in 2 to 3, heat comes out 4 to 1, but because this is constant pressure and the volume is expanding, there's also work going from 2 to 3. And the textbook, or this problem, gives us a bit of a hint there, because it says, consider the expansion stroke of a diesel engine which has a compression ratio of 20 and a cutoff ratio of 2. So there's, I don't know, maybe it doesn't really give us as much of a hint as I thought, right? But there's two different work processes, right? Determine the temperatures, determine the total work done, determine the total heat supplied, derives all equations starting from the ideal gas relationships to phase. So I'm going to start. So A, so A we did, right? I'm going to leave this till last because I like to do the symbolic stuff first. Because I think that I can demonstrate more understanding in a smaller amount of time if I do it that way. So the total work done, work per cycle, is equal to the work from state 1 to 2 plus the work from state 2 to 3 plus the work from state 3 to state 4. Because that's why it's nice to draw the PV diagram first, because I know that there are three different work processes, right? So now, that means I got to do the first law. Because now, so again, I asked myself my 3 questions, right? So the energy benefit and energy cost. This is thermal efficiency, which they don't actually ask me this, although I don't know why they don't ask me to do this, because first they ask me to find the total work and the heat in, so it would not be hard to do this, but this is going to be work per cycle divided by heat in. My second question is, are the processes open or closed? We will assume they are closed, right? And my third question is, what's the fluid? And it's going to be air, which is an ideal gas. Right? They give us a hint there because they say use the ideal gas law, right? So the first law is going to be E at the end minus E at the beginning is equal to Q from beginning to end minus W from beginning to end. Right? But we're always going to assume that there's no kinetic energy change, no potential energy change, no spring energy change, right? So this is really just going to be mass times U at the end minus U at the beginning is equal to Q from beginning to end minus W from beginning to end. Okay, so if I'm going from state 1 to state 2, then this is not too bad, because Q from beginning to end, as I move from state 1 to state 2, is equal to 0. That means that the work, right, because this is negative work, so this becomes M times U at the beginning minus U at the end, right? So work from 1 to 2 is equal to the mass, which is constant for the whole problem, times U at the beginning, U1, minus U at the end, which is U2. I'm going to skip to 3 to 4 because it's the same. Also, Q 3 to 4 is equal to 0. So work 3 to 4 is equal to M U3 minus U4. Unfortunately, from state 2 to state 3, this is not a simple process. Remember, a simple process is one where there's either heat or work, but not both. But here, there's heat and work. So our lives are a little harder, right? But we remember that work is equal to the integral. So in this case, work from 2 to 3 is equal to the integral from 2 to 3 of P dV. Right? And luckily for us, the pressure is constant. So that's the pressure. I'm going to call it 2, 3 because it's the same at 2 and at 3 times the integral of dV from 2 to 3, which is pressure times V3 minus V2. But I want to multiply by mass so that all my terms kind of look the same. So this is going to be the mass times the pressure times V3 minus V2. Right? Or if I multiply the pressure, because it's P3 and P2, they're the same. So I'm going to say mass times P3 V3 minus P2 V2. So the net work is the sum of all these three things. Oops. W net is going to be the mass, which is multiplied by all of these things, times U1 minus U2 plus U3 minus U4. I don't mess around with what the signs are going to be. I know that the work in, that this one I expect to be negative. The work out, I expect this to be positive. But I just let the first law take care of all of that stuff for me, right? And this is going to be, again, this is going to be plus P3V3 minus P2V2. You know you messed up the signs if you see how my state 3 stuff is positive and my state 2 stuff is negative. If you have a sign mismatch, it means that you messed up one of the signs, right? So you just add these three things up. You let the first law worry about the sign. So this is going to be the mass times U1. Well, I'm going to drop those inner brackets because now I'm just going to group by state number minus U2 plus P2V2 plus U3 plus P3V3 minus U4. This is going to be equal to the mass times, U1 minus H2. Remember, this is the definition of specific enthalpy, is U plus PV, plus H3 minus U4. So this is my symbolic solution anyway to whatever part that was, part B maybe. I'll put a box around it. Well, hopefully a reasonable facsimile of a box. I don't know any of this stuff yet though. That's the downside here, is that I don't know the mass, I don't know U, I don't know H, but if I did know all those things, then I could find the network. Now what's my heat in? For this, we go back to heat in happens between state 2 and state 3, right? So we go back to this, right, where because for all of our processes, we assume that kinetic energy and potential energy and spring energy are 0, right? So this is going to be that mass times U3 minus U2 is equal to Q minus W from 2 to 3. But we know W from 2 to 3. And it's equal to the mass times, which one gets that? H2 minus U3. No, that's not right. I'm trying to do it all in my head first. This is not good. You know, you don't have to remember it because I wrote it down already. That's the beauty of human civilization. We learned how to write stuff down, right? So the work from 2 to 3 is the mass times P3V3 minus P2V2. Right, but I'm trying to solve for Q23. So Q23 is equal to the mass times U3. Right, now this was negative, so I just move it, the sign stays the same, plus P3V3 minus U2 plus P2V2 mass times H3 minus H2. Now, it turns out these are almost exactly the same equations you would get for a diesel cycle or for an Otto cycle problem, except remember the two states, H2 and H3, which are on the horizontal line on my PV diagram, they became enthalpy values. Not because there's anything magical about it being horizontal, but because of the math, right? And this is exactly how I want you to think about exams. You want to show your work, right? Start with the base level of the first law and move through all the states, right? So now we are going to determine the total work done. Oh, this is the answer that they gave us, right? So now there's some information, so let's try to draw a state table, right? 1, 2, 3, 4. Temperature. Now. Oh, yep. What's your question, Jules?
So I just had a quick question about U and H. So we had some kind of a similar problem on one of the homeworks last week, and I forgot that H was
U
equal
plus
to it's U plus PV, and I think I had calculated the V
Yep.
values.
You can,
the
there's nothing wrong with
specific,
doing that. You'll get the same
volume.
answer. It's just a lot more work.
Okay. Yeah, I think it was a little bit different
Sure,
just
yeah.
because
Yep.
of rounding and stuff. Would that be
Yes,
okay
it would
on
be
the
okay
exam?
on the exam.
Even
If you
it
did it that way, it's still correct. I think that you might run into problems doing it that way on the exam because it's a lot more time consuming. So, it's a timed event, but it's still correct. So we want temperatures and pressures at least, right? So let's see what they tell us. So consider an expansion stroke which has a compression ratio of 20. So we know that compression ratio goes from 1 to 2. So V, it's always the biggest one over the smallest one. V1 over V2 is equal to 20. I could probably put volumes over here too. And a cutoff ratio, so that's cutoff ratio goes from V3 over V2 is equal to 2. At the beginning of the process, so I think that when they say the beginning of the process, they mean the beginning of the expansion stroke. No, So here they must mean, so at the beginning of the process, the initial temperature is 627, and then it expands at constant pressure. So this must mean T2 is 627, but we want to turn that into Kelvin. So 627 plus 273, you've all done this in your heads probably already, but I used my calculator, is 900. Right? So, excuse me, hopefully that doesn't persist. Anytime you get an air cycle problem and they're telling you temperatures in Celsius or Fahrenheit, automatically convert them. Right? I also like kilopascals instead of megapascals. And the air expands at constant pressure. So P2 and P3 are at 6.2 megapascals, but I want these in kilopascals, right? So that's 62 kilopascals. No. Right? So this is 6,200 kilopascals, right? 6,200. Until a cutoff volume to ratio 2 to 1. Then the air expands adiabatically with no heat transfer until it reaches a maximum volume. Determine the temperatures reached at the end of the process. So this, I think these bracketed numbers, we're not supposed to know those, as well as the end of the expansion process. I think that's just the answers. Determine these other things. Derive all the equations, the internal energy and the enthalpy change for ideal gases. Use specific heat values. So CP is equal to, for 1,000 K. So I'm just going to say CP is equal to 1 kilojoule per kilogram Kelvin. CV, so I know that CP over CV is 1.4. So 1 divided by 1.4, it's about 715. So I'm going to say 0.71 kilojoules per kilogram Kelvin. You could look it up in the textbook if you wanted to. So I'm also going to assume here that we're pulling air in from just the environment. So here I'm going to end exhausting air to the environment. So I think that this is going to be 1 atmosphere or 100 kilopascals. And this is going to be 100 kilopascals at the end. No, that's back to state 1. So the pressure is not necessarily the same here. Okay, so, but we might not need that. Maybe let's leave it blank because they didn't tell us this. So let's assume that we don't need it, right? So this one's tricky because they don't tell us. I like to start at state 1, but they didn't let us start at state 1, or at least they make it look like we can't start at state 1 because they don't give us the information. But so if I knew T1 and P1, right? That's usually, but I don't know either. But I can still examine my process as I go from state 1 to state 2. Here we assume ideal. And if I did the second law here, I'd see that delta S is equal to Q over T plus sigma. But it's adiabatic as I go from state 1 to state 2. And it's ideal, so there's no entropy generation, which means that the mass times S2 minus S1 is equal to 0. And that's only interesting if the mass is not 0. And so this is 0. So this is isentropic. And because it's isentropic, I can use my isentropic relationships. The problem sort of tells us to do constant specific heat, but I'll at least write the equations down for variable specific heat too, right? So constant specific heat, and this is the one that I always mess up, but I'm pretty sure that I'm going to get it right. I have confidence in myself, right? T2 over T1. Now, because this is a closed system process, that compression ratio is not a pressure ratio, it's a volume ratio. But I think these get inverted. So this is V1 over V2. I can, to the power of K minus 1. I can always check because my temperature should go up as I compress the fluid, right? V1 over V2 is positive. This is R, right? And K is 1.4. Usually, I do this to find T1, right? Or to find T2. But I don't know. That's not the thing here, right? Because now I know T2. I don't know T1. And I know this volume ratio. If this was a variable, well, I'll go through into the end here. Right, so now if I'm trying to find T1, it's equal to T2 divided by V1 over V2 to the power of K minus 1. Right? So this is T2 is, we converted that already, I think it was 900 degrees Celsius, right? 900. So this was a good problem to pick because this is not usually the way that I do these problems, right? And then this is R, which is 20 to the power of K minus 1, which is 0.4. So I'm going to take 20 to the power of 0.4, invert that, times 900, and I get 271.5 Rankine. If I was doing this as variable specific heat, I think this now doesn't invert, but you might want to check. So this would be that VR1 over VR2 is equal to V1 over V2. This is 20. So then here I would solve for VR2. No, VR2 right? VR2 is going to be known because we know T2 goes to A22 and find VR2. And we can also find, while we're here, we might as well find H2, right? So VR2 is going to be VR1 over 20. But that's not what I want to do. I want to find VR1. So it's still the same equation. You can see how when you get the information a little bit differently than what you usually get, it's good to slow down. So now I'm trying to find, so here I know VR2. I know this together is R. So VR1 is equal to R times VR2. And once I know VR1, then I can go to A22 and I want to find U1. That's why I like to do the symbolic solutions first. Because if I didn't do the symbolic solutions first, I have to find U1 and H1, right? But now that I've done the symbolic solutions, I know that I need U1 and I know that I need H2, right? So that's how I would do it that way. But that gives me only the temperature. If I need to find the pressure, I'm not necessarily convinced that I do in this problem, but if it asked me to find the pressure, then I would use the ideal gas law from state 1 to state 2. And here, can I do this? So that would mean that P1 V1 over T1 is equal to MR, but that stays constant. So that's P2 V2 over T2. Now I'm trying to find P1. So from here, P1 is equal to P2 times V2 over V1 times T1 over T2. And now that I have found, so V2 over V1, this is 1 over 20. T1 and T2, now I have those two values. So then I could find, and I think they told me P2, right, was 6.2 megapascals or something. So then I see that that I get a value for P1. Does that sound good? So it's a little weird because we had to go backwards, but that's okay. Now I'm going to go from state 2 to state 3. This is the heat addition. Is it isentropic? No, it's not. So I can't use the isentropic relationship, but it is an ideal gas. So I've already used the first law to get those equations, right? But I can use the ideal gas law. So P2 V2 over T2 is equal to P3 V3 over T3. But P2 is equal to P3. This is the nice thing, and it's good you have to show that you know why, but the volume ratio V3 over V2 is equal to the temperature ratio T3 over T2. And they told us this was RC, which is 2. So T3 is equal to 2 times T2. Right, so T2 was 271.5. No, that's T1. T2 is 900, right? So then T3 is 1800 Kelvin. And P3 is the same as P2. Right? So only 4 states, and we did 3 of them already. But we're about to go into the hardest one. So now from 3 to 4. There's a little bit of sleight of hand in the diesel cycle. And you maybe remember this, you maybe don't. Right? But here we can use this isentropic. So now, as I move from 3 to 4, this is isentropic expansion. Now we know that delta S is equal to 0. So that means I can use an isentropic relationship. Usually the isentropic relationship that I'm going to use here is that T4 over T3 is equal to, and again, I believe this inverts, so you might want to check your equation sheet, but this, I believe, should be V3 over V4, oops, to the power of K minus 1. Here's the trickiness. So there's a couple of things we want to know. Remember the diesel cycle. Pressure versus volume looks like this. That's not the best drawing, right? But as I go from 1, 2, 3, 4. As I go from 3 to 4, right? Then I see that the volume of 4, there's 2 things that I need here. The volume of 4 is equal to the volume of 1. So that means that V3 over V4 is equal to V3 divided by V1, right? But now I'm going to multiply both sides by 1. But the 1 I'm going to multiply over here is V2 over V2. Right? So V3 over V4 is equal to V3 over V2 times V2 over V1. This is the cutoff ratio, which is 2. This is 1 over R, which is 1 over 20. Right? So this is 2. Well, I won't skip this step. This is RC over R, which is 2 over 20, or 1 over 10. So then I'm going to put this back into this equation here. T4 is equal to T3 times 1 over 10 to the power of k minus 1. So I take 1 divided by 10 to the power of, let's just, this doesn't make sense, to the power of 0.4 times T3, which was 1800. And this is good, this number got smaller, 716.6 Kelvin. So now I have all those temperatures, which means that I can put them back in here, or at least the constant specific heat versions of these. So now if I use constant specific heat, then this is going to be mass times, it's a little weird, right? Because it's going to be, I want to put the U's together, so this is going to be Cp times T1 minus T4. That gets the U's together, right? And I'm going to say plus, oh, this would be Cv, I'm sorry. Because Cv goes with U, and this is Cp times, now because I said plus, it's going to be T3 minus T2. And this, in constant specific heat, is going to be mCp T3 minus T2. And now I know Cv, T1, T4, Cp, T. So I know everything except I don't know the mass. That means, unless it was given, I don't think it was given. So I'm looking for a place where I know the most. Because to find the mass, I've got some strategies, right? If I knew I know that volume is equal to mass times specific volume. So if there's some place where I knew the volume and the specific volume, I could find the mass, right? If I knew work or heat transfer, then I could use the first law. But usually, if this is an ideal gas, then I'm going to use the ideal gas law. But I got to use it kind of the messy way, right? So now I'm going to say that maybe I will add a page at the beginning here. So I know that P, V, is equal to M, R, T, where R is equal to the universal gas constant divided by the molar mass. This is on the reference sheet, first page of the thermal tables. This is going to be on table A. Is it A1 or A2? Pretty early in the book. Or A2, A1E, A2E, right? So that's how you find R, if it's not just given to you. Right? We're trying to find the mass. So mass is equal to pressure times volume over R times T. So I would like to have a place where I know the pressure, the volume, and the temperature. But I'm not sure. Oh, that's why. Because even though it says determine the total work done, it's the total work done per unit mass. Because we don't actually have enough information to find this anywhere. Usually I would look at the state where I know the most. So there I know the temperature and the pressure. But in this case, there is no volume. Right? So here, we would be more explicit on an exam. I would say something like determine the total work per unit mass during the expansion stroke. right? And then I would also put the units of what you're looking for here. So here, because they gave us the answer, we can see that they say total work, but they really mean total work per unit mass. But if you had to find the mass in a problem like this, then you would use the ideal gas law. But the units are going to be tricky because this pressure is going to be in, I like to put it in kilopascals because that's kilonewtons per meter squared, multiplied by volume, which is going to be in meters cubed. R, I'm pretty sure, is in kilojoules per kilogram degree Kelvin. We'll see if I got it right. Because you can always check with the units. That's what makes them. It's like cheating, right? Which you're not allowed to do on the exam. You're allowed to use units, but you can't cheat. Kelvins cancel, right? Kilonewton meters, when I put these together, right, is kilojoules. That cancels with this, and I get 1 over kilograms, which is the same as kilograms. So when I do ideal gas problems like this, I like to put this in kilopascals, because that's kilonewtons per meter squared, and R ends up being... But what if this was an imperial problem, because this is, again, the unit part of the problem, right? Then we're going to have, this would be in probably pounds force per square inch multiplied by cubic feet. They could give it to you in cubic inches because you're talking about a cylinder, piston cylinder assembly, so maybe, but let's take the worst case scenario here. So then I'd have to take that and multiply by 12 squared inches squared per foot squared. I'm going to look up R, well, I'm going to look up or calculate R, and it's going to be similar to this, but instead of kilojoules, we get BTU per, instead of kilograms, pound mass per degree Rankine. And then this is going to be degree Rankine, right? The Rankines are going to cancel. The inches squared are going to cancel. Foot cubed divided by, but now when I put these together, I have foot-pounds force, so I got to take this and say that I want a BTU on top, BTU per 778 foot-pounds force. That cancels with this, right? And then this BTU cancels with the BTU, and I'm left with 1 over pound mass, right? And this is why no one likes the imperial system. Well, it's not true that no one likes it, but no one in this class tends to be like, yes, it's a problem in English units. So that generally is how you go through and do one of these diesel cycle problems. The Otto cycle problem is very similar, but it's a little bit more straightforward because you don't have, if this was an Otto problem, then this would happen at constant volume, and you'd come down here. So you would only have heat addition there, and you wouldn't have any work, which makes the problem a little simpler when you go through and do the first law. You get very similar equations. The terms are all in the same order when you think about the state numbers, but they're all specific internal energies. There's no specific enthalpies in that problem. Does anyone have questions about this problem or about internal combustion engine problems in general? Okay, I guess we have a choice now. We can, so when we think about, so now here, we did this one, right? We did this one, and we did this one. So the ones that we haven't reviewed are kind of a Brayton cycle with all these components, right? Although there is an example that's a Brayton cycle with all those components, which is pretty much the most complicated Brayton cycle you're going to see, and then a vapor compression refrigeration cycle. So I have a couple questions for you. The first is, do we want to do review of those two cycles? And then the second is, would you prefer to do review of those two cycles, or at least try to do the Brayton cycle today? And do you want to meet on Thursday, I guess, is maybe the next question. Do you want to meet on Thursday, or you want to push through and do a Brayton one tonight? Often when I do review, we end up not really doing this one, but if people would like to do that one, we can do that one too. Oh, in the chat here. Okay, so how about we stop for tonight and we go through. So can someone volunteer to pick out a Brayton cycle problem? So I think we have 2 people that haven't volunteered yet. So if someone can go through the textbook and find a Brayton cycle problem. So if you haven't volunteered yet, if somebody could do that, and then if somebody else could find the heat pump problem. So if you can divide those out, that'd be great. Because I know what's on the exam. So who would like to bring in the Brayton cycle problem? It's funny, I'm not sure if it's less comfortable when I do this in a classroom or on Zoom. So everyone's going to have to bring in a problem because there's 2 people who haven't brought in a problem yet. And there's 2 problems we're trying to bring in. Yes, a Brayton cycle, and try to find a complicated one. It can be like this one, or it could just be something else that looks weird. You know, like sometimes in the textbook they just have, I think it's more for Rankine cycle ones, but they have some weird, like, oh, there's this thermal process that's pulling heat away from it. Do you want to try that one, Esmond? Perfect. So then, Gurpreet, if you could find us either a vapor compression refrigeration or a vapor compression heat pump cycle, then we will be good to go. Sound good? All right. I will see you all on Thursday. Cool. Bye-bye.
Thank you so much. Have a great night.
Yeah, no
Thank you
problem.
so
You
much.
too.
Have a great night.